So welcome to the second web session for Chapter 4, Regression. We're going to continue with the exercises that are from the book. So we're going to start down here with 5 through 9. So download and use this data set. So if you click on the words this data set, it should download credit card.xls. I'm going to go ahead and open that up and then go back and look at the questions. So number 5 is build a simple linear regression model with annual charges as the dependent variable, that's our y, and annual income in thousands of dollars as the independent variable, that's our x. Then I want you to interpret the regression equation in r-squared value. Then I have you do similar things for 6 and 7, which is, again, we're trying to predict the annual charges on the credit card, but now we're going to use household size. And then in number 7, we're going to use the years of post-high school education. So these are just simple linear regressions. So if we look at the data set, you have an account number. There's a data dictionary over here too that helps, right? Unique number identifying account for this credit. Annual income for the household in thousands of dollars, the size, number of people living in the household, years of post-high school education, and all this other stuff, right? All right, so now we want to try to predict the annual charges, which is in column I, and the first one was using annual income, I believe. Yes. So let's do the following. Let's see if I can insert a scatter plot using those two. All right, we got 5,000 data points. So it looks like a big mess, really, right? Big blob there in the middle. But there does appear to be some kind of upward trend to it, as in the more money you make, the more you're going to put on your credit card. Right? You can afford to put more on your credit card, I guess is one way to interpret that. I'm going to go ahead and delete that. I don't really need it right now. And so now I'm going to go ahead and do a regression. So remember, you go to data, data analysis, and then pick regression. Our Y range is annual charges, so I'll select all 5,000 records, including the header row. The X range was over here in B. All right, and I selected the header row, so I need to check off labels. New worksheet apply sounds good, and that's all I'm going to do. All right. So we see that the r-squared value is about 31.5% of the variation in the annual charges can be explained by just the annual income for that particular account holder. All right, and we can look at the p-values on each one. So on annual income, it's saying it is statistically significantly different than 0. So what this is saying is that every $1,000 extra that I make a year, I tend to put another $121.35 onto my credit card, this particular credit card. Right. So overall, looking not too bad, right? 31.5%. What was the rest of the question? So estimate the estimated regression equation. So I just did that. Right, that was what this number means. What does the 3146 mean? That means if I don't make any money at all in annual income, I will still put $3,146.36 on my credit card. In this case, that probably doesn't make a whole lot of sense. In many of the regression equations, when the x variable is 0, right, that's the y, the intercept becomes the y-axis intercept. It doesn't make a whole lot of practical sense, but it needs that to be able to do the rest of the equation. And again, the r-squared is 31.5% of the variation in our credit card debt or charges can be explained by annual income. Okay, so the next one was, so this was number 5. So let me rename that. And the next one wanted household size. Yes. So I can run a regression again, and instead of in B, it's going to be C. Sometimes I like to type instead of using the selector tool. And this one is showing that only 3.5% of the variation can be explained by the size of the household. It is still statistically significant. This 5.17e to the negative 41, that's 0. It's saying move the decimal over 41 places to the left. So that's just a rounding error. That is 0. So what it's saying is for every additional person I add to my household who's living in the house, I yearly put on $551 approximately. Right? This model is not as good as the other one in terms of explaining the variation. Right? So if we plotted that, it would look even more of a mess than the one that we plotted before. Number 7, we're doing simple again, this time years of post-high school education. So it might be a good idea to think about, okay, as I have more post-high school education, do you think I'll put more or less on there? You could run a correlation between those numbers and see what they get. You could do a plot. Let's do a plot just for fun. And let's just see what it looks like. Why does it look like that? It's because the years of post-high school education are whole numbers, only 0, 1, 2, 3, 4, 5. Apparently they don't go past 5, which is odd. But we do kind of see a downward, so if we added a trend line, right, we would see a downward slope. Right. Let's see if I can move this up to see it a little bit better. So it's only 1.6% of the variation can be explained by this, is what this is saying. So let's run the actual regression and see if that's what we get. Let me just move this out of the way. And then let's do another regression. This time we're in D. Click OK. And here's the 1.6% that we saw before. All right, it's a little bit more digits out to the right. It is still statistically significant. That means statistically significantly different than 0. And it's saying that as I increase in years past high school in education, I will actually spend less, or actually put less money on my credit card. In this case, about $510 less for each additional year. So looking at those 3, we see that the first one we tried was the better of those 3. Right? Of course, we have lots of other variables, right? We could combine all 3 of those, or we could look at some of the other variables there too. So let's see, I forget what I asked you for in number 8. Build a multiple linear regression model with annual income, household size, years of post-high school education. Oh, so with those 3. Perfect. All right, so let's do that. So if we go back here, and we run a regression. This time I am going to go ahead and use the selector tool. So now I want B through D. I have labels, new worksheet apply. Alright, this is number 8. And now we see that our adjusted, when we move to multiple regression, we move away from the R² value to the adjusted R² value. They're very similar in this case, because the adjusted R² adjusts for one thing to adjust for is the number of observations, and the other is the number of independent variables that go into it. So we went from 1 to 3 independent variables, right? So to adjust for that, the number of observations stayed the same. So we see that we can explain about 36.3% of the variation in annual charges based off of these 3 independent variables: annual income, household size, years post high school. So overall, is the model significant? We look at the significance F. That is a 0. So yes, overall the model is statistically significant. And then we look at the individual statistical significance for each of the independent variables. We will always leave the intercept in regardless of whether or not it's 0. In this case, it is 0. So annual income is 0. This is 0. Remember, e to the negative 57 is a really small number. Here, e to the negative 28 is a really small number. So they're all 0. So all of these coefficients, estimated coefficients, are statistically significantly different than 0. That's what those p-values are telling us. So we would want to leave all those in. We increased our explanatory power by about 5% by adding the other two, the household size and years of post-high school education, into the model. All right. So the question was also something: interpret the estimated regression equation adjusted R squared by. So now we know how to do that. B is a little different than what you may have seen in a previous stats class or anything, but it's somewhat important. Do the estimated slopes differ substantially from the estimated simple linear regression equations you calculated before? What does this imply about multicollinearity in the multiple regression model? Confirm your conclusion by calculating correlation coefficient between the 3 different independent variables. All right. So let's start with the first question. Do the estimated slopes differ substantially from the estimated simple linear regression equations you calculated before? So in the simple linear regression, the x variable is the slope coefficient, 121.355 in the annual income. In the multiple regression, these are slopes of hyperplanes because we're in more than 2 dimensions. So it's kind of hard to visualize, but just think of it as a slope. 120.63, not that far off, right? Like half a dollar, right? 50 cents. For household income, it's 550, about 551. Here it's 533. Again, not off by that much. Post-high school education was negative 509, negative 505 here. So they're very, very close to what we had estimated before. So they don't differ very much. So then the second part of that question was, what does this imply about multicollinearity? Well, for this you have to remember what multicollinearity is. It is correlation, high correlation, between independent variables, so between the x's. We do not want that to happen because it means that those 2 variables are probably capturing something underlying that's the same, and we don't want that to go into the model. It can mess things up. So we want correlation between the x variable and the y variable, but we do not want high correlation between 2 different x variables. So because the slopes did not differ, do you think that means there is multicollinearity or there is not multicollinearity? Hopefully you said there is not multicollinearity. If they differed a large amount, then we would think that there's probably some interaction between those 2 x variables where it would show up, right? So we think that there's not multicollinearity. We can confirm this by calculating correlation between the 3 different independent variables. So let's do this. Let's go back here to credit card and see if we can. So we want to calculate correlation between annual income, household size, annual income, years of post-high school education, right? And then household and years of post. So those are 1, 2, 3 different ones we have to calculate. So we could do that manually if we want. There's a shortcut though under data analysis. If you go up to correlation, click OK. input range, we want these three grouped by columns, labels in the first row, new worksheet apply, okay. And let's look, it'll just give you the off diagonals, right? So this is saying annual income is 100% correlated with annual income. That shouldn't surprise you, right? It's comparing to itself. Household size compared to annual income, only 0.01, so very close to 0. So basically no linear relationship. Household size to itself, of course, is 1. Years of post-high school education to annual income is slightly negative, but again, pretty much 0. And then years of post-high school to household size is also pretty close to 0. So there's no strong correlations, positive or negative, between those three independent variables. Now, it only gave you the lower half of this stuff because remember, correlations, doesn't matter which order you do it in, you get the same correlation coefficient. Doesn't matter the order of the arrays, the x and the y you put in. So let me rename this correlations. This is number 8b, I believe. Yep. All right, so that tells me that there's no multi-collinearity in that model, which is good. That's what we're looking for. All right, now we get to number 9. Add age, a dummy variable for gender. So I need to create a new variable called something, right? 1 if it's female, 0 if it's male, and a dummy variable for whether or not they've exceeded their credit limit. 1 if yes, 0 no. So I'm going to add 3 different variables. Do these independent variables substantially improve the fit of your model? Based on your conclusion, what are your next steps? All right, so let's go back here. All right, so I want to add age, gender, and exceeded, which has a typo in it, to the model. All right, I'm not adding hours per week watching television. It's kind of in my way right now. So what I'm going to do is move it. Remember, I'm moving it because I need all of the x variables next to each other. All right. So I'm also going to insert 2 columns here. And call this one female and say equals if this equals female, return a 1, otherwise 0. And I can autofill it all the way down, do a couple spot checks, 0, 1, 1, 0. All right, looks good. And then exceeded. If I2 equals yes, return a 1, otherwise return a 0. And autofill all the way down. Here's a yes. All the others are no so far. So now I have 1, 2, 3. There's 3 original, and adding 3 more variables. 2 of them are coded variables that I just did. 2 dummy variables that I coded to the model, and they have to all be next to each other in Excel. In other statistical software packages, that's not necessary, but in Excel it is. So let me do data analysis and go back to regression. Click OK. And instead of D, it'll go E, G, E, F, G. I don't know my alphabet. And click OK. It thinks that I wanted that. Oh, because I inserted stuff. So it's annual charges for that. And then B through G should be okay, I think. Let's see what happens. All right. So let's see if we got the right stuff. Looks like it. Okay. All right. So now what we have is we see the adjusted R squared is 36.368%. What was it before? 36.31. So it went up a little bit, but not very much. It only went up 0.07%. So that didn't really help me much. Overall, the model is statistically significant. We see that the p-values on annual income, household size, and years post high school all stay statistically significant. However, we see that age, whether or not they're a female, and whether or not they exceeded their credit limit in the past 12 months, at the 5% level, alpha equals 0.05, they're all insignificant. So what that means is age is not statistically significantly different than 0, the estimated coefficient of negative $8.79. Practically, this is probably also true. Over the year, do I really care if I'm the credit card company if I'm off by $9, right? For a female, whether or not they're a female, this is saying if you are a female, you holding everything else constant. That's important when you're talking about multiple regression. So holding everything else constant, if I'm a female, the amount that I put on my credit card is about $155 less than if I was a male. But that's not statistically significantly different than 0. So it doesn't really help us much. And then whether or not I exceeded in the past 12 months, if I did exceed in the past 12 months, then I actually put less onto my credit card for the year. All right, so that's almost statistically significant at the 5% level. If I used alpha equals 0.10, 10%, then it would be statistically significant. So overall, the model, the amount of variation that can be explained did not go up very much, 0.07%. And the 3 new variables I added in didn't really help me much. They're all statistically insignificant at the 5% level. So what do? So what are my next steps, right? That's what that last question is. Well, I would probably go back and start trying to look at the other variable that was in there, which was, I think, something about watching TV. Hours per week watching TV, right? And see if that does anything for me. Yeah, it looks like to me I would go back to the model with just 3 independent variables. I would not stick with the 6 for sure, right? One is it's more compact and easier to explain, and the other is those 3 are not statistically significantly different than 0. So it would be interesting for you, and you could try this now. Add hours per week watching television. You might drop those other 3 and just add the other one, hours per week watching television, and see what you get. See if anything interesting comes out of that. So this is number 9. So that covered quite a bit of material in a very short time. We looked at simple linear regression, doing a multiple linear regression with those same variables in, checking for multicollinearity, both as a sanity check and also doing the actual correlations between them. We found with those 3 we did not have multicollinearity. And then we added some more variables. 2 of them we had to code as dummy variables or binary variables, indicator variables. And remember, we had to make room and put them in the proper spot so they were next to each other. And then concluded that it probably was not worth adding those 3 as predictors for our annual charges for this particular data set. So that should get you through the rest of regression, and you should be able to easily do your Excel assignment and quiz at this point. Good luck, and keep plugging along.